gonna edit that out.
No, probably not. Because it's just y'all, and I don't care. Y'all are fine. You're fine. You need to cut off your throats. A ball is thrown horizontally from a height of 100 meters with an initial speed of 15 meters per second. How far does it travel horizontally in the first 2 seconds? This is a lot easier than you think it's going to be, right? Because what is it really asking for? What variable?
Delta X.
It's looking for delta x, right? And easy peasy, okay? Because if it's thrown from a height of 100 meters, is it going to hit the ground in 2 seconds?
No.
It's like accelerating 9.8 meters per second? No, in 2 seconds it's not going to. So what you've got is a situation where ball is being yeeted off the thing, but after 2 seconds, it's only going to have gone a certain distance, right? And that certain distance is our delta x. So we don't even need to worry about the y stuff here, correct? So let's talk about what we know. We don't know delta x. We do know time, 2 seconds. We do know that our velocity of x is what? 15 meters per second. Somebody want to do that in your head real quick? It's going to go 30 meters.
Oh, shoot. Yeah.
Big 5 number 1, delta x equals v times t, right?
Equals 30 meters.
Okay. X equals 15
Allow
times 2.
me.
So that was easy. Sometimes they are easier than they are going to make you think they are, and this is one of those times. Doesn't always happen, but it's nice when it does. All right. Any questions on that? Okay. Am I already in your happy place?
Yeah.
Okay, that's good. All right. Let's look at 19. Okay. A javelin.
I used to do javelin throws.
That's cool. Travels in a parabolic. It's like the only track and field event. Well, it's one of very few track and field events that you could actually like use those skills to kill another human being if you had to.
Whoa.
I guess you could do it with a discus or a shot put or a hammer or something, but you know, I mean that's what a javelin is. It's a thrown spear. It's a weapon. Yeah, that's right. Javelin travels in a parabolic arc for 6. I guess if you're a wrestler, you're also learning like practical people hurting skills. That's cool. In a parabolic arc for 6 seconds before hitting the ground. Compare its horizontal velocity 1 second after being thrown to its horizontal velocity 4 seconds after being thrown.
Wouldn't it be the same?
It would.
So you would just say it would be the same.
Yep.
Look at me go.
Number 20.
You probably should take
We are going through this like champs.
Yep. Because like I said, these are probably a little too easy, whereas the ones on that other paper are a little bit too hard.
Great.
Okay, now this one right here, this is decent. A circus performer is launched out of a cannon with a launch angle of 30 degrees and an initial velocity of 40 meters per second. How long after launch will it take for the performer to reach the top of his trajectory, and how high is this point? Finally, we've got a problem that is worthy of our attention. So let's start with a picture, okay? Circus performer launched out of a cannon. I'm not going to try and draw a cannon because it would probably end up looking dirty. So I'm just going to draw a parabolic path, okay? And we are only interested in the first half of that journey, correct? We are only interested in the upward part. And so we know that the initial velocity is 40 meters per second, and we know that the angle from the horizon is 30 degrees. So if we take this initial doohickey down here, and we turn it into a triangle, we're going to have 40. We're going to have the x part, which is going to be our v of x. And we're going to have the y part, which is actually going to be our VO of y.
Holy.
Oh, plus the 30-degree angle.
Yes, thank you. The 30 is our angle on the inside, and then this, of course, is the right triangle.
So let's, we could do.
So it wants to know how long after launch will it take for the performer to reach the top of this trajectory. So we are interested in this portion in the time going up, right? We are also interested in how high he is going to be, so we are looking for delta y. With me so far?
Yeah.
Okay. So let's first of all describe what's going to be happening to this poor clown. So have you ever heard the one about the human cannonball? He got hired and fired in the same day?
Ah!
Yeah.
Yeah.
So describe what's happening to him in the x. Once he is shot, does his velocity in the horizontal change? It does not, right? What about his velocity in the vertical? As he goes up, what happens?
Yeah.
Gravity pulls him down. So he is being accelerated which direction?
Yeah.
Downward, right? So we know that his acceleration is going to be negative 9.8 meters per second.
I have a question.
Yes.
It's a little off topic, but it has to go off this side. So like rockets,
Yeah.
whenever they're going up, you know, and that like the rockets pushing them up, are they still being accelerated downwards?
Well, gravity is trying to accelerate them downwards, so there's going to be a gravity downward force, but there's also the rocket engines which are accelerating them upwards.
And then whenever it gets in space, there's not gravity acting on it anymore. So which way is it being accelerated?
Well, it depends on how far up it goes. See, actually what's happening for most things that we put in orbit is the gravity is acting on them. So they are in free fall, but they're also moving forward. So as they fall, they're also moving forward at just such a rate to where they maintain a circular orbit.
Oh, like whenever you spin the ball.
It's like satellite. It's like you're falling, but you never hit the ground because you keep falling around it.
Oh, so it's like whenever you have a little back.
Yes.
Okay.
And sometimes they need to do subtle force corrections by increasing the forward thrust so that they stay in orbit and don't crash back down to the earth. But if you have too much, then you're going to get out of orbit and you're going to end up leaving you. So it's all very, very sensitive balance of forces there. Does that answer your question?
Yeah.
Okay,
Yeah.
good question. So in our y component, do we know VO?
No.
Not yet, but we can get it by triggering out this triangle, right? Do we know VF?
Yes.
For the top half of this, what is VF going to be?
Oh,
It's going to be 0.
oh. May I ask why?
Because at the top of the arc, right here, it's going to stop moving upward and it's going to start moving back downward.
Oh, okay. So that's when the free fall begins.
Yeah, no. Free fall begins the minute it leaves the camera.
Okay.
Free fall just means the only force acting on it is gravity. Okay, so it's in free fall from the moment he's fired until he hits the ground. Since we're just looking at the upper portion of this, now we want to try and find delta y. We want to try and find t. Okay? So, where do we want to go and how do we want to try and solve this?
Would we use the total?
Use big five number 2 to find time? Except
Wait, you don't have
we don't have an issue yet, but we can get there.
Would we use the
So we are going to come to big five number 2 in just a minute, but how are we going to find our initial velocity?
So for total.
So up, right. Okay. Bless you. Let's talk about what we know. We know our hypotenuse. Here's our theta. And this over here would be our opposite, right? So who do we need?
We need the opposite.
So we're going to use sine. Okay? So in this case, the sine of 30 is going to equal our VO over 40. So then you go to your handy dandy calculator. You go 40 times the sine of 30. Be sure you're in degrees. And what do you get? 20. Very good. So our VO going upward is going to be 20.
to type VF, you could use the afterboard and do offset like
Oh, we don't have to have the X for this. I mean, if we wanted to find it using, we could use the Pythagorean theorem to find it, sure. Okay? But we have enough now to find time, and then we have enough to find delta y. Or find delta y and then find time if you can find a way to do that. But, excuse me. Oh my lord. Okay, I'm back. Jasmine had suggested using big 5 number 2, and I think that's a great idea. Big 5 number 2, VF equals VO plus AT. Now, if we wanted to rewrite that to solve for T, how would we do it? Okay. VF minus VO divided by A. I love it. T equals VF minus VO divided by A. Now, it's handy that VF minus VO is going to give us a negative number, and acceleration, since it's going the other way, is also a negative number, right? Because a negative divided by a negative
it's a positive.
is going to give us positive, and we can't have negative time. Okay, we can't move backwards through time, unfortunately. Not yet.
Not yet.
Yeah. I haven't figured out a way to do it. So when we start plugging this stuff in, our VF is 0, so we got 0 minus 20 divided by 9.8.
Would it be a negative 9?
You're right.
So that would count.
It's going to be awfully close to 2.
Yeah,
Right. 2.04? I love it. So 2.04 seconds. Sweet. Come back up and let's put that in as our time. Okay. And for our delta y, what do you want to use to solve for that?
Big 5 3 would, or I mean, big 5 4 would be easiest because then that first part cancels out. Because
Okay.
VF is 0.
Also true. So you could use big 5 number 3. You might also consider using big 5 number 1.
Yeah.
Okay.
Oh, yeah.
If you, because you take average velocity times time, so your average is going to be VF plus VO divided by 2. So 20 plus 0 divided by 2 is going to give you 10 for your average V, right? Your average V of y is 10. And so if you do 10 times time, which is 2.04, I get 20.4 meters, right? Questions? I skipped a couple steps up on the thing there, but does that make sense? Okay, good.
Yep. I was trying to work the math out in my brain.
So, not wanting to take all the fun away from you guys, I'm going to leave number 21.
So that's an A and a B. Yes, it is.
But there could be an A and B in the other one.
Okay. Could we work it out on the board?
I mean, there was technically an A and a B in number 20. Yes, you can totally go work it out on the board. I'm just not going to interfere with things. So, can I go ahead and flip to the next slide for y'all?
Y'all want to work it out as a class?
Yeah.
Can I do the writing?
I don't
Yeah.
All right.
All right.
All right. So, now, do you want me to keep recording?
I'd rather not.
All right. Then I guess I'll hit stop.